And in particular, I would like to introduce some of our work based on RF interferometer for biomedical detection and identification. Okay, Donna, she's not here yet. She is working. Her work is somewhat related to this type of interferometer. Then on Thursday, we will go to discuss about some of the bolts and nuts issue, the specifics about high frequency electronics. That's the plan. Okay, so today in the beginning, I would like to go through some background information with you, and hopefully we can look at this the development background and understand why I think lab-on-chip is probably the major technical driver for the future of our area. Okay, and what are the challenges there? And then I would like to share with you, okay, what kind of activities we have in terms of working in this new area, right? And future work. So my hope is, okay, by the end, you guys think, oh, this is fun, and you would like to get into this area. And better, if you would like to apply for graduate studies here, right, in Clemson. That's my hope. Okay, so before we start, here I say radio frequency, which basically means a frequency covers from 3 kilohertz to 300 gigahertz. Okay, sometimes I mention coating free, which means I don't coat any sensor surfaces with the biorecognition molecules. Okay, so as electrical and computer engineers, we are very proud about the work we have done in this area, right? Electrical and computer engineers have helped to change the world. You know that. Everyone knows this, right? Everyone benefits from this. And I think we know that the driving force behind that revolution, technically, it's something called scaling. That's the driving engine. Scaling means the transistor gate sizes keeps getting smaller and smaller and smaller. As a result, we know that the transistors work faster and faster. For the same amount of chip area, then you can put more and more computing powers, right? The devices together. So we know Moore's law. And as a result, you know that after how many years? That was the first patented electric computer back in 1946. So today is 2014, right? We know the Intel computer chips, Intel inside, right? So after 60, 70 years of development, we have successfully shrunk the room full of computing devices and the machine on a chip, right? Which is a lot more powerful, a lot more energy efficient, a lot more cheaper, right? Okay, so this is behind the revolution we just mentioned about. And unfortunately, that exponential growth is coming to an end, okay? The reason is, you see, predicted by 2017, which is only 2-3 years from today, the gate size, physical size, will be on the order of 3 nanometers. That's fairly close to the size of atoms. They are on the order of 0.3, right, 0.4 nanometers. So we don't know how to shrink atoms yet, right? So probably we will run into a hard limit. So in terms of shrinking the size of the transistors, then what are we going to do? especially for you guys, right? Very young, you have a great professional career in front of you. So what specific areas or what great opportunities are out there, right? What can we do? Then look at the old time where the development of electronics have been focusing on digital, so-called digital electronics, okay? So that shrinking process was single-minded just for the speed and energy of information processing for computer chips, okay? Now, because we have this limit there, so many people are beginning to think with this infrastructure and the momentum and with the silicon, which is a very good sensing material, not only a very good electrical material, okay? It's a top sensing material. It is a very good actuation material, actually. So what can we use them for? Okay, then people found you can actually use this for biological, mechanical, chemical, power, photonics, all different types of applications. And then you can actually integrate them together. As a result, maybe we are entering a new era. People actually gave it a name called more than more. So the older time is the Moore's law governed time, right? Where we know that the computing power doubles every 2-3 years, right? The price drops down every 2-3 years. That was Moore's time. Now it's more than more, which means it is now the time for us to make use of what's available and for functionality integration. Function integration, okay? There are many proposals in this integration era, okay? You can, I don't think I have a slide here to show you. Some impressive examples are like a nuclear power plant on a chip. Yeah, people put radioactive materials on a wafer to integrate with your computer chip, for example. Then the radioactive materials, they will decay, right? They have lifetime, like 50 years. Then you can design some structures to capture those high energy particles and use that as a local power source for your circuit operation. Imagine like in Lhasa, or if you want to travel to other places, and then if you have such a nuclear battery, you don't need to worry about battery for 50 years. That's good, and it's demonstrated, okay? Nuclear power on chip, and that's very impressive. And also impressive work like heard about the accelerator, right, guys? They put accelerator on chip as well. Okay, but here today what I would like to share with you more in detail is this so-called lab on chip vision. Okay, that is, I think, inspired by the development of computer technology, because we said, okay, for 40, 60, 70 years, people put this room full of a computer and on chip. Now, similarly, people would like to put this room full of analytical capabilities on a single chip. Okay? Do you see? They are in parallel, right? And the goal here is to integrate the biomedical and the chemical analysis capabilities of that lab and put that on a let's say quarter size computer chip, and to analyze, for example, cells, molecules, okay, and then what for? To address some of the grand challenges we are facing. The first one, for example, the global health. if you can integrate the capability of that analytical lab, clinical analysis lab on your small device, then probably the patients or the potential patients, they don't have to go to wait in line for so long, right? They can monitor their own health or disease at home, right? So they can send their information through wireless everywhere now to their doctor's office, right? The doctors may look at that and say, hey, you need to come and see me, or don't worry, you just drink water, take a rest. You don't have to come here and wait, right? That's one possible application. Another one is, let's say, environmental monitoring. You probably know that, like water, ocean, fresh water, and specifically like in China, the air pollution. And this was reported by the China Daily. And it said in the next, how many years, I forgot. I remember the number. The monitoring air quality in China, they're going to spend about $800 billion to address that issue. It's a huge, let's say, economy, business opportunity, and it's a huge technical challenge and opportunity as well. And there are some issues in other countries, like India, right? And also people talked about like lung cancers. I think the number is about 7 million patients every year. Lung cancers mainly due to like air pollution. Yeah, there are smokers, but the majority actually is caused by pollution there. So if we can use what we have in electrical computer engineering to develop techniques to help address these issues, that's a great area to get into. And security, we know that. And now when you get into the airport, right, they use millimeter wave scanning right now. That's part of the application, high frequency. And there is the urgent need for, let's say, chemical weapon agents detection at high sensitivity, okay? And toxic industrial chemicals and all other applications where we need, for those applications, we need the analytical capabilities, okay? So now, we would like to integrate those capabilities, put that on a single chip, okay? Now, you look at this lab, actually you need people there to do the work right now, right? They need to think about what kind of measurements we need to do. And that's intelligence, right? In terms of intelligence, it is said nothing beats CMOS. Okay, you can prove that. More or less rigorously prove nothing beats CMOS. CMOS is the technology to go in terms of intelligence there. So today is somewhere here. So for $1,000, you can purchase the equivalent computing power of maybe close to a monkey. Okay, and for future development, you can probably get to that of some primates, close to that of a human being. Okay, that's electronics. And the second type of capability you need to have in this lab is you need the capability to take your sample, move your sample around, right, for different testing. You need that. Then for that part, look, we have microfluidics and nanofluidics. You can move cells, you can move single molecules around for the testing. That's microfluidics, nanofluidics. Okay, all these techniques are so-called CMOS compatible. They can be built on your computer chip use your computer chip technology to build them. Okay? So you have the intelligence now, you have kind of, right? We need a further development. You have the mechanical capability to move things around. You actually need a third type of capabilities, right? That capability is, okay, how do I know the molecule or the cell I'm looking at under microscope, that molecule or that cell is dangerous to human health? How do I know that, right? Is it a virus, or is it a bacteria, or is it just a healthy cell? How do I know? So that's detection and identification. That's the third type of capability we need to have, right? In a lab there. Traditionally, for the third type of capability, people use optical-based technique, like microscopy and flow cytometry, two of them. Okay, two of them, and you still need very high sensitivity, so you can see the cells, you can see molecules, and the sensitivity actually is normally fairly low for optical-based technique. The reason is the optical frequencies are too high, so your materials cannot follow the high frequency motion, so they don't have strong interactions, so naturally then you don't have super high sensitivities. That's why if you look at cells under your microscope, it's difficult for you to tell your cell from your liquid environment. The contrast is very low, right? Then what do people do? Label, right? Fluorescent labels. That also provides you with something called specificity and selectivity. Okay, labels, like especially for molecules, you have to use labels. Otherwise, you can't see them. All right. Yeah, people also develop a lot of different types of nanoparticles for that process, for the labeling. Another way is you use something called surface functionalization, what I mentioned a moment ago, coating. What do people do here? Instead of labeling the cells or molecules you want to analyze, you put your bioregulation molecules on your sensor surface. So when you have the target molecules or cells, they will be captured by your bioregulation, let's say, molecules. Then look at the change of your sensing surface. You know, okay, I did capture this type of cell, this type of molecule. Then you can tell, okay, this type of cell is dangerous, or this type of object is a virus. That's how you can do. Either way, they are not user-friendly, okay? The cost can be very high because you need especially trained people, right? Like in a lab to work on these things. Don't expect an 80-year-old gentleman at home, not very agile, to be able to do those things at home and do the observation and inspection himself, right? So the cost and size is always an issue there. Yeah, there are very active research efforts to miniaturize those microscopes and those flow cytometers. In particular, they would like to put these things together with your cell phone, because right now on the market, we have about 7 billion cell phones in use today, okay? So from the very beginning, the first cell phone to today's cell phone, in total we have about 15 billion cell phones, okay, produced so far. That's a huge market, okay? And if you can miniaturize those things and they can be attached to your cell phone, maybe that's a step forward in terms of reducing the price and make it more convenient to use right? To move to the mass production and general consumer market. Yes, it is a big step, and as I said, it's a very active research area. But it's optical. Your resolution, you will suffer still, especially when your cell phone does not have that high resolution power, right? Like a NAB microscope has. And you still need the labeling process. Okay? So, how about electronic approach? Because I criticized optical approach, right? Yeah, people thought about that and have been very active trying to address the problem from electronics point of view. Like a prominent technique is something called silicon nanowire transistors. You build nanowire transistors, like what Dr. Rod Harrow explained to you guys in the device lectures. And then you still coat the transistor surface with the biorecognition molecules. These people have proved, yes, you can detect single molecules this way and recognize them. That's cool, that's good. Of course, you have some issues. The issues are, it's actually quite challenging to build such a device, a transistor. And also, you are restricted in terms of what kind of sample you can use. Because if you use a physiological sample, you have a lot of ions, electrolytes in our body fluids, right? They will actually block the sensing of these transistors because the ions can move fast enough. They will agglomerate, let's say, on this transistor surface. So the transistors can't see the molecules. Then people are thinking about, okay, is it possible for electrical engineers? We can build some devices, find some technical approaches which don't need labeling on the surface, on the sensor surface, and don't need fluorescent labels of those molecules. Is it possible? Nobody knows, but people have been trying, okay? And it's possible, it's promising. Two pieces of work to introduce to you here. This one is by this Texas Anderson Hospital, okay? What they did was, okay, you measure the size and the electrical capacitance of white blood cell subpopulations. And this tells you if you can measure them reasonably accurately, you don't need your cells, you don't need to label your cells, and you don't need to coat your sensor surface. You can tell them apart, right? If you find something here, then you know, okay, this is this type of white blood cell, right? You can. Then if you build an electronic device with this, you can have a blood analyzer. It can find wide applications, okay? Blood analyzer. And there is another recent publication which measured 4 different types of protein molecules in BSA buffer. It tells you that if you can measure over a wide frequency range and get sufficient amount of information, hey, actually you can more or less tell them apart. Okay, then you don't need to label them. You don't need to coat your sensor surface with the biorecognition molecules. All right? And there are many smart people, they are in our area as well, right? They try to build electrical flow cytometer. Okay, instead of using optical approach, they use just 2 electrodes, and this is called differential detection, right? Yeah, this is a standard. They compare with the standard technique. It is partially successful. You can see some differentiation of the white blood cell subpopulations, but not quite there. The main reasons are They measured only at the 2 frequency points and fairly low. Okay, so the information contents are not sufficient for them to detect, to identify those white blood cell subpopulations. When you work at lower frequency, like a megahertz we just saw, you could have some issue, which is the cell membrane will block your probing fields. So any information inside your cell you cannot see because of the shielding of the cell surface, cell membrane surface. Okay, that tells you, hey, you needed to operate at a higher frequency. So it's like an X-ray, right? Higher frequency, so X-ray can see through objects or see through human body. Similarly, you need to operate at high frequency, so the probing fields can see through cell membrane and know what's inside your cell. The purpose is then you can get more information of your cell. Okay. Many people in the high frequency electronics area, they are trying to do this. Okay, let's work on high frequency and try to measure cells. Then you have 2 approaches. One is something called a broadband measurement, because we said you need a broadband measurement to have more information. At the same time, you need a high frequency to see through cells membrane to get more information, right? Unfortunately, for the broadband measurement, the sensitivity is limited, okay, so far. How about a higher sensitivity measurement where the general technique or approach is to build resonators or cavities? Yes, people build this type of resonator. That's probably the most sensitive one, called whispering gallery mode resonator. Okay. And next time when you see Professor parameters to resolve these problems. This is the first interferometer, first generation. What do? You have a probing signal comes in, and you split that probing signal into 2 branches. Here is the material under test. This is the reference, okay? And if the 2 branches are symmetric, okay, and you have a differential cancellation mechanism built in with this structure, so-called rat race hybrid. Okay, and then you don't have anything out. They cancel out each other. Destructive interference. However, if you introduce a cell or a molecule at a material under test, then that difference will come out. Okay. What do you measure? You measure something called scattering parameters. Okay, that is a terminology for high frequency electronics. Okay, it's a different language there called scattering parameters. It's basically transmission transfer function. Okay. So we then went down to understand the operation with different fluids, and yeah, it turns out this can be a very sensitive technique, and a few times more sensitive than currently people reported. And this device is also passive, which means we don't use transistors type of thing inside. So it's called scalable. Scalable means you can like shrink it or enlarge it in terms of geometry. And it's also scalable in frequency, which means you can make it work at 1 gigahertz. You can make it to work at 100 gigahertz. So other group, like this group in Germany, they built 240 gigahertz sensors, and they said, okay, they modified from our gigahertz sensor. Okay, then this probably is our second generation of interferometer. We built the interferometer and tried to detect single yeast cells. And turns out, okay, dead yeast cells and live yeast cells, they do have different properties. So that says maybe it's possible you can detect and identify yeast cells, live ones or dead ones, right? Without labeling and without coating your sensor surface. This is our third generation of interferometer, because you see our first and second generation where we still operate at a single frequency, even though we operate at higher frequency. Okay, single frequency, the information is limited. If I just single frequency, that's noise, right? I don't communicate with you with anything, but I need this multi-frequency, the wide frequency range to get my message across. So what do? We need that wide frequency operation. Then our third generation interferometer, where we introduced tuning components inside the circuits, the interferometer. So you can tune two things. The first one is the sensitivity. The second one is operating frequency. So you use the phase tuning phase shifter to tune the operating frequency, and you use the tunable attenuator to tune the sensitivity, because sometimes you may not want that sensitive sensing. Okay. All right. And also, the measurement is electrical, right? We said it's something called scattering parameter, transmission coefficient. So what does that mean in terms of my molecules or my cells, right? So what's the connection between your electrical scattering parameter and my material property, right? You need some algorithm to make a collection, right? So we developed the algorithm. Yes, it is related to your structure. And specifically, you need to know, we call this permittivity, which basically describes the polarization of your sample or your cell, your molecule. Okay, we need to, and how they respond to different frequencies. We called dynamic properties. Okay, we can measure them and obtain them. Yeah, this is an example to show you we can tune over a wide frequency range at operating at a very high sensitivity, and this is a zoom in figure just to show you, if you zoom in, what you see. This is where your starting point. You don't have the sample in, you have DI water on both branches, and then you have methanol a little bit. You introduce another type of material. So you can see actually the concentration level for both methanol and 2-propanol, they're the same, but the response is different because they have different voices. Okay? All right. Yeah, you can talk with chemists and physicists, build models, and to obtain some other properties such as the relaxation time, etc. And move on. By measuring at multiple frequency points, you can actually identify in your DI water what is the percentage of methanol you have, what is the percentage of 2-propanol you have. So in other words, you can actually identify the molecular components inside your solution, even though the solution is well controlled, okay? It's not like the solution from my body fluid. It's very complicated there. There are thousands of different types of molecules, etc. We can't do that yet. But under this controlled situation, we can, okay? And yes, we on the 3rd generation, we built some other different types of interferometers with different capabilities. And yeah, glucose, we can measure glucose at a concentration level which is a lot lower than people can do right now. Okay? And this is what I meant. We can obtain the glucose molecule, for example, if you poke them, how do they relax back to the equilibrium condition? And we also measured, for example, DNAs, damaged ones and undamaged ones, where the concentration level is so low that the distance between 2 DNA molecules is on the order of 8 micrometers. Keep in mind, our structure has about 7-8 micrometer gaps. So in total, we measured about 1 nanoliter volume. DNAs in that, it's 40-50 DNA molecules. We can measure that reasonably repeatable, reliably. Okay, and once again, we can tell in a controlled solution how many damaged DNAs you have, how many undamaged DNAs you have. Okay, all right. That is possible by measuring over a very wide frequency range. Okay, so if you compare the technique we are developing against the traditional ones, right? The optical techniques, for example, on the market, because that's our competitor, or some other new techniques which are under development. So where are we? This is an optical technique where you use nanoparticles for something called a surface-enhanced Raman scattering technique. Yeah, we are at least about the same sensitivity, at least, okay? But we measure at many frequency points, right? I said we give you a whole range of voices of the materials you are measuring, okay? And if you compare that with this surface plasmon resonance technique, okay, where you can have very low, very high sensitivity, very low concentration level measurement capabilities. You know, we are compare against them. We have at least once again about the same sensitivity. Once again, we have a lot more information, and we use electronics, which can be directly integrated with CMOS techniques. There are some other techniques very interesting, like I guess I'm not sure if you guys heard about like nano resonator. You build resonators like a mechanical beam or at nanometer size, and then you can trap one molecule and measure that molecule. There are also whispering gathering mode optical resonators. They can measure single molecules, yes. But under very strict environment requirement, okay? And they measure at one frequency point. All right? Yeah, that is a line of wire device we talked about. Okay, here's another optical sensor. We are probably better than this. Okay, that is the interferometer development so far, and the interferometer application for cells, molecules measurement. And if you think about what we have been measuring, it's clear we are measuring the polarizations, I said, right? And the dynamics of these polarizations. That's called electrical properties, right? The same or similar interferometer can be used to measure magnetic properties. Think about it from an electrical engineer point of view. All the materials, you describe them by two groups of properties, electrical and magnetic, right? Is there a third one? I don't think so, right, so far. So we are measuring the electrical, now we are measuring magnetic properties. Magnetic properties, basically you measure from electrical engineer point of view, and the mu, which is permeability, which has two components, the real component and the imaginary component. And then you want to see their frequency dependence. The measurement is based upon something called a Zeeman effect. I guess some of you heard about that. Zeeman effect is you apply an external magnetic field, okay, and it split the energy level, okay, and then you measure that. So traditionally, that is something called ESR, electron spin resonance spectrometer. Okay, it's about 1 ton. Okay, you can do the measurements. That is a basic piece of equipment for chemists. And they have a lot of limitations. For example, you need to use helium most of the time. And some of you might have heard about the helium crisis. So we don't have enough helium. If you can help them address those issues, it will be great. The limitation for their system is their sensitivity is limited because they use cavities. Their Q value is on the order of a few thousand. If you call our interferometer Q value, it's on the order, it can be on the order of a few milli. Okay, it can be a lot more higher. And also this operates at one frequency, we operate at multiple frequencies. You can have a lot more information. And you can use field modulation instead of, or you can use a frequency sweep. Some issues, yeah. We would like to try to reduce the size and the cost. Yeah, we built simple structures where if you zoom in and look at the devices, this is how it looks like. And put some and put some sample here, and you measure the shift of the operating frequency and the shift of the transmission coefficient. The shift of transmission coefficient is associated with the absorption. Okay, the shift of frequency is associated with the mu prime, the phase shift caused by the sample. So we can obtain both simultaneously. Okay, that's not possible for the traditional EPR, ESR, the big one. No, it's impossible. And as I said, we measure over wide frequency range, not just one frequency point there. Yeah, if you think your frequency is one decade, right, from 1 gigahertz to 10 gigahertz, that may not be wide enough. If you need a wider frequency range, what are you going to do? Yeah, you can put frequency bands together. That's what I show you here. Yeah, we can measure from about 20 megahertz to 40 gigahertz. And actually, we went down to a few megahertz already. Okay. And yeah, this can be further lower because our system can go down to a negative 145 dB. Yeah, this is related to something called dynamic range of your system for electrical engineers. Dynamic range means so how wide the signal variation you can measure. Okay, the thermal noise will be your dead end, right? Bottom. So which is, if you measure over a 1 hertz range, it is negative 175 dBm there. So we still have few tens of dB to reach there, but it's getting much harder to go close to the thermal noise limit. Okay, yeah, we hope we can get to, I hope we can get to maybe 200 kilohertz, and we would like to get up to terahertz. We're working in both directions there. Now, I mentioned this in our research, right? You need a very large dynamic range. So probably Dana knows this already, because it's so sensitive. It's not so easy to use actually, because if some of you walk around, you can imagine you could shake the floor, and that will change your measurement output. That's bad, right? You don't know that is caused by your material or it's caused by a vibration somewhere, right? Then what are we going to do? That means your equipment will be confined within a lab environment, right? So our target is to help the public to be able to use that at home, right? Then we would have to find some way to sort of amplify, to enhance the sensitivity without requiring such a large dynamic range. Yeah, we are on our way. We found some techniques. For example, you can use the same technique as you guys heard about the invisible cloak, right? It is awarded for this, what is that award? Covenant or some award for the invisible cloak. The military is very interested in that. So you build the material, you actually hide some of your equipment. Okay. Use similar technique. We modify, so you can modify how fast your waves travel in your structure. Imagine you have a piece of, you have a cell here, right? What is going on is, you have the microwave RF propagating through and interact with your cell. And that interaction will generate loss and phase shift. So you measure the loss and phase shift. That's your information, right? If you can make the same wave moving slower, so you have longer time to interact, that's a possible approach for you to improve the sensitivity, right? Because the interaction is a lot stronger. That's one. The second one is this. For the same amount of probing power, the same amount of voice I have, if I can focus somehow, okay, enhance my field and locally, I don't waste my energy somewhere else, so just interact with this cell. I can probably improve my sensitivity, right? That's what we do. We use something called a metamaterial. That's the material in optical frequency range, they call that, they use that to build an invisible cloak, right? Yeah, we use that to do this type of measurements. Yeah, we prove that for some of the design, we can increase the sensitivity by maybe 40 dB, which is 100. That's 10,000 times. Then we can reduce the requirement for the dynamic range. Okay? So, all right. That is what we have done. So we are reasonably happy about what we have so far. Then what are we doing now, and what about the near future, right? So we would like to, as I said, expand that to terahertz. And we would like to miniaturize and automate the whole system. Actually, Donna here is helping us to in the automation process, right? She already wrote some LabVIEW code, right? Help to control these some of the pieces of equipment, because right now we do measurements with we use our hands to twinkle the sensitivity and the tuning process. We would once again would like to automate that process. All right, and what else? We are also trying to build an array structure. So to use that to image the surface domain of something called GUV, giant unilaminar vesicle. It's a mimic of cells. So you build the cell size GUV, but it does not have a nucleus. It only has the membrane. And that membrane, depends upon your molecular components, you will form different domains. So that domain we would like to measure. Currently, people measure that. Okay, they use fluorescent labels, but the problem is the labels will interact with the other molecules, so distort the process. Hopefully, RF does not interfere with the natural process there. Yeah, the second one we are working on is particle and cell analyzers. So then hopefully it's inexpensive and high speed. And we hope we can demonstrate the measurement of a single molecule. And another piece of work we are working on is to develop sensitive sensors to measure chemical warfare agents or toxic industrial chemicals. Currently, the workhorse is this type of device called ion mobility spectroscopy. That's the workhorse. But its sensitivity is limited and it's bulky. And people are developing micro devices, and they have achieved a sensitivity like 1 part per billion for a simulant of nerve agent, sarin. And looks like we have the potential to be better than they are. Okay, and yeah, we are building the detectors for gas chromatography. Okay, and we are building the detectors for high performance liquid chromatography. Okay, yeah, and I think this is my last slide for terahertz, electron spin resonators, resonance spectroscopy, and we don't need a whole room full of equipment. Okay. Oh, the last slide is yeah, actually malaria. We would like to check if we can measure malaria in patients whose red blood cells are infected, and then we will have paramagnetic materials there. That's the signature for this type of patients there. Okay, so in the end, we are developing radio frequency lab-on-chip techniques, which is a part of the bigger lab-on-chip activity. And I believe that is probably a major technical driver for the future of my area, of electric computer engineering. And yeah, there is a lot of work to be done there. I think I would like to stop here. Thank you for your attention.
Thank you.
Do you have any question for me? yeah, when you are thinking about the questions, I can say, yeah, we are trying to integrate like an oscilloscope on wafer or network analyzer. Oh, I do have a network analyzer on wafer and high voltage sources on wafer, just next to your digital computing circuits. Okay, that's yeah, part of the work we do. And then hopefully we can, in the future, we can have a whole integrated system. It's like your cell phone type of thing, or it's a add-on to your cell phone. Then you can just have your sample, whether it's body fluid like saliva or air, right? Suck in and tell you, okay, this you don't have gas leakage in your kitchen, or you don't feel well, but it's fine. Maybe you are just tired. You don't have virus in your saliva. You don't have bacteria in your saliva, right? So that type of application. Okay. Yes.
Why did you pick malaria for that research?
Good question. Why do I pick malaria? It is for money. The reason is this: Gates Foundation had a big push for malaria control, right? To eliminate malaria for African and some other places. And yeah, we found that our technique could be used for that particular application, and it could be better than what they have now. So we wrote a proposal, and they found us to work on malaria. Specifically for malaria, they use the golden standard is to draw the blood of the patient and put that on the slides, right? They call it smear, and then read, count. Okay, out of 1,000 red blood cells, I have 150 with those black dots. That's the gold standard today. So if you, yeah, there are people who develop a optical technique, try to count, right? You can use your camera, can use this one. The image processing, all types of techniques you can count. But we believe, yes, we can measure, because the malaria patients, they have this magnetic hemosome that is specific to those patients. So if you can measure that, then you should be able to tell. Okay. Right now, what we obtained is for a bunch of them, you see some trend. I cannot say right now that we are able to measure malaria with 98% or a given percentage of accuracy. I can't say that yet. And if we can measure that, if we are sensitive enough, you probably don't need to draw the blood. You can just put your finger, right? These are two pieces of electromagnet, and then do your measurements. Okay. Thank you.
So
Yes.
I have a question, a real quick question on that bottom right-hand picture there. So when someone sticks their hands in that cavity, you're trying to test for the presence of malaria, and how exactly does it sense it?
That's the dream, yes. And you could argue, okay, the finger would be moving, a lot of potential practical issues. Yes. And then when the finger is sticking into, you do two measurements. The first one is without the electromagnet on, right? You measure that. And you probably read a spectrum, that's in 1 minute, 2 minutes. And then you turn on the electromagnet, because the malaria patient, the blood is circulating, right? So this, I learned that under your fingernail, actually you have a lot of blood. And in total, actually, on average, about 20 microliters of blood. Then some of the blood, red blood cells, are infected with the malaria pigments. So the pigments are there, so they are magnetic. And so you apply strong external magnetic field, then because of the magnetic property, pigment there. So the response will be different. So you compare these two, then you should say, okay, maybe this patient has malaria or needs further check. Okay, that's the idea. Yes?
I mean, so I guess this is not related to this particular aspect of the project, but I was wondering about the whole issue with silicon versus graphene sheets and how many people are trying to move towards graphene sheets. I don't know if you have.
That's a good question, actually. I don't have experience working on graphene. Unfortunately, if I knew you would ask me this question, a few days ago I was at a conference. There was a panel discussion about graphene. Is that a fantasy? Or is that just what? The interest for physicists and material scientists, or it's the real future, right, of electronics? Unfortunately, I didn't go. I was at another lunchtime meeting. I am actually not very sure about that. Maybe Dr. Rod Harrow he would answer your question better than I can. But my personal feeling is this. My personal feeling is that CMOS is already giving you and me the rich resource and potential, and if we can make use of that resource and the potential, I think at this moment I may not need graphene. Okay. Sorry, I don't really know. And the reason is this: it's not only an issue of how fast the transistors can work. There are many other issues associated with that. If you want to make that particular material or device working like silicon do. For example, right, I'm not sure if Dr. Rod Harrow had time to tell you guys, in terms of device speed, the 3-5 materials are much better than silicon, than CMOS, right? That's still the case. Yeah, like indium phosphide. Yeah, they are faster, but they never took over the market. Even though worked hard, right? People worked hard. There are many reasons, a few. Correct me if I'm wrong.
Since I was a graduate student.
Right, but it's still not there. For the gallium arsenide, right? Gallium arsenide, like Dr. Rod Harrow just mentioned, I remember when I was a student working in a clean room to build devices, I had one person there working on a piece of substrate on gallium arsenide. He said, "Hey, don't touch my substrate. It's expensive." I said, "It's about 1 by 1, 1 centimeter by 1 centimeter." I said, "How much?" He said, "About $1,000. Look, I have a 4 inches wafer. That's $20, right? And it's difficult for the industry to make large size wafers for the gallium arsenide. So it never took over CMOS, even though it is faster, right? It is faster. And also, I think maybe Dr. Rod Harrow told you guys, like CMOS took over because you have this complementary, right? PMOS and CMOS and NMOS. So you can, energy-wise, you have the advantage. So for graphene coming back, I am not sure. For example, the process, the P and N and the doping, how do you modify them? I'm not sure. But I think you probably could use graphene for sensor application. It's like carbon nanotubes. I worked on carbon nanotubes myself. It is inspiring. The material is good, but it's so difficult to handle, right? Yeah, tomorrow, on Thursday, I will show you some one slide where carbon nanotubes I try to work on. And They say carbon nanotubes can be a very good inductive interconnect type of thing, okay? There are hundreds of papers talking about botanic carbon nanotubes for something called a future interconnect application. But the hundreds of papers are based upon a theoretical prediction that was predicted maybe in 2002 by the UCI, University of California, Irvine professor. I just forgot his name, okay? Yeah, I know he graduated from Yale, okay? I just forgot about his name. He wrote a paper, it's a theoretical prediction, said, okay, this methanic carbon nanotube has this property, blah, 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 okay. And based on that, hundreds of papers. Even today, we can't have the experimental verification of the properties that he predicted. It's difficult to put your hands on, okay? So, but that's good. Yeah, it's nice you guys are pondering about those new developments, right? And then try to find which area you can enter and work for your career, right? Your profession and career. That's good. Okay. Thank you, guys.
Any other questions?
Oh yeah, we have another 10 minutes, right?
I have one other question.
Yes.
I may have missed some of this, but you were comparing the optical techniques to the RF techniques, and fundamentally, why do you think optical techniques aren't best? Or compare the difference. What's the fundamental difference?
What's the fundamental difference between RF and optical techniques, right?
And why one's better? You and I have had these discussions before, but I just thought it would be interesting to elaborate on it a little bit.
Sure, that's a good question. I'm not sure if I can answer, but anyway, I'll try. I think for optical techniques, because we have optical instruments with us, I think that's the starting point. We have our eyes, we see optical stuff. So we condition our brains that way. In terms of physics and for sensing applications, I don't see why optics are better. The reason is if you look at first of all, if you want to have better sensitivity, you need to have stronger interactions, right? And if that stronger interaction comes for electrical engineers as this something called permittivity. If you look at the permittivity of all the materials at optical frequencies, they are all about the same. Like the N for water, the refractive index for water is about 1.419 or 3, and the refractive index of protein DNA is about 1.42 something. So that difference is very small, and they are very small, and the difference is very small. And so, which tells you the interactions are relatively weak, right? So in physics, it should not give you very strong interactions, not a very high sensitivity sensors. But if you look at the microwave range, water permittivity is 80, and the dielectric permittivity of protein DNA maybe 4 or 5. So you have a large difference. So that gives you a contrast. On the other hand, the 4 or 5 is much, much bigger than the 1 point something. Well, because the air is 1, right? So that should give you a lot stronger interactions. But the problem is that the legacy, the momentum from optical area is there, difficult for you to overcome. So you have to have something they can handle, right? So then you can take over. For example, for me, Microsoft put some new operating system out. I don't want to change to the new operating system, even though it's much better than my old ones. I want to stay with my old ones, right? That inertia is there. And that's just, it may not be a good example, but that's the situation.
So the bottom line really is the permittivity of the materials and their differences.
Yes.
So the sensible.
Yeah, that's the basis for the sensitivity. Maybe optical stuff, I think microwave can do the same thing. You just shine light and something is reflecting back to you, right? You don't need any collections. Electrical way, previously you have to have wires or collections, right? You cannot do that remotely, right? But now we have wireless communications. I think you can make them small enough or versatile enough. Maybe it can help you there. Okay. So sorry for those optical people. Okay, that's just my prejudice, and otherwise I cannot. I would have to change it to optical area, right?
Other questions? Girl, let's thank our speaker.